Other thing, in between sort of last class, I want to touch on, Chris and I had a conversation about sort of this idea of Bayes factor bounds, or this idea of prior probabilities and things along these lines. This is a tricky thing. I'm not a Bayesian statistician. I don't have a full, sort of a minimal grasp on the general types of things, but with the incorporation of that Bayes factor bound statistics I'm having that you all calculate, it starts to become relevant with things, right? But this idea of prior probabilities and posterior probabilities is kind of tricky, right? Because what I'm saying is like, oh, here's the prior probability, but here's the probability, and so this is the probability of the alternative relative to the null, assuming that both of these things are equally likely. That's a hard thing to wrap your head around, because if it was equally likely, why isn't it friggin' 50%, right? If we're taking a Bayesian approach, if we're talking about a prior probability, we're talking about the probability of some event based on existing knowledge, based on all the information that we have available to us. What do we believe the likelihood of sort of event versus non-event being? Okay, that's going to be our prior. Our posterior probability, this is the probability of the event that we've calculated once we've collected the data. So once we've got the data collected, what do we think is going to, what do we determine the probability to be, right? So if we're thinking about prior probability, if we're assuming that winning football games is a perfect indicator of who's the better team, right? If we're, let's say we've got a series, let's say NBA Finals, right? If we're saying who wins the finals is sort of roughly associated with who's the better team, right? And so prior to the NBA Finals, we have some probability, right? Some guess of who's more likely to win relative to somebody else, right? That's going to be our prior probability. Now, posterior probability is at the end of the series. We know who's won. We've got our discussion. Now, we can't say that that's perfect indicator of who's the better team, but our estimate of who's likely the better team has probably changed once we've actually run the data out and actually taken a look at this. Okay. So one way to think about this. Remember that confusing example I took you through that was part of Cohen and Neal's thing, right? But this actually is a nice example of working with prior probabilities and the impact that priors have on the calculation of posterior probabilities. Remember in this example, what we have is we were looking at base rates of schizophrenia and a different screener that we have, right? And we know just from our epidemiological work that the likelihood of someone having, just a randomly selected person from the population having schizophrenia is about 2%. So this is a very, very unlikely event, right? I think that seems high, but whatever, we're saying 2 people out of 100 lifetime diagnosis of schizophrenia, that seems high, but I don't know. Anyway, this is what it is. So this is our prior probability. So prior to collecting any information, any data, right, we're saying that the likelihood of grabbing someone with schizophrenia from my sample is 2%, right? People following with me on the idea of the prior, okay? So what we then have is we have a screening measure, and it looks like a pretty good screening measure. Sensitivity, our ability to correctly identify the criterion. That means if there's someone out there with schizophrenia, will this screener capture it? Yeah, that's pretty good, 95%. So sensitivity is saying of the people who have schizophrenia, we're going to capture 95% of them with our measure. Specificity, how well does our measure detect non-criteria? For people who don't have schizophrenia, how good is our measure at capturing those people? Again, pretty good, 97%, right? And so if we're looking at this, we would say, and we talked about this in terms of what we do with null hypotheses testing. Remember, the question we're asking with our null hypotheses test is, assuming that the null hypothesis is true, what's the likelihood of obtaining these data of this characteristic or more severe? And so that's what's being captured here in our sensitivity specificity. The problem is this isn't what we really want to know, right? Probably what we want to know is that what's the probability of the null given the data that we've had, right? We get the opposite. We get, assuming that the null is true, we get the probability of the data. What we really want to know is based on the data that we've got, what's the likelihood that the null is true. If we want to ask this is a completely different scenario, right? And so here, if we flip this around, so here the probability of a positive test, assuming the probability of a positive test, assuming that the null hypothesis is true, or that someone doesn't have schizophrenia, is going to be 0.95 minus, or 1 minus 0.95, so it's 5%, right? Seems super rare. But what we're actually interested in, probably, what's the probability of a normal case, or what's the probability of the null given the data that we've collected? So what's the probability of a normal case given a positive test? And this is where we talked about those two things aren't interchangeable. Here, if this is the question we want to get, this is where we get into Bayesian types of stuff, right? Where we have to take into account this prior probability of schizophrenia. And if we do this, if we assume a prior probability of schizophrenia of 0.02, the likelihood of obtaining the likelihood of a positive test in the face of a normal case is actually not rare. It's actually really, really common, okay? And this gets into positive predictive value and negative predictive value, turn this on its head, right? And so we go through, remember we had said, so if I'm looking at the probability of my sensitivity is going to be 949 divided by 979, right? My sensitivity is going to be 20 divided by 21, right? But if we go the other way, we take 50, we've got 30 positive tests. Of the 50 positive tests, 30 of those tests were normal, actual normal people, right? And that's where this comes in, okay? And so when we're talking about this Bayes factor bound, the idea is that assuming that the null, or assuming the alternate hypotheses and the null hypotheses are equally likely, okay? Even Steven, what's the greatest evidence, or the greatest ratio, or the greatest likelihood of the alternative relative to the null, okay? And now the crux of this issue, and I've gone through and sort of looked into this, Bayes factor bound is super controversial. Bayesian statisticians don't like it, because they're basically, you're just trying to conflate sort of p-values, which is a frequentist thing, and Bayesian statistics, they don't care for it, right? And part of what happens is if we start to change this prior probability, right? We had talked about how sort of the reason we're getting such a different sort of probability here based on what we kind of think is going on, was what is actually going on, is in large part because of that prior, right? This is an unlikely event. If we go through and we say, okay, the likelihood of randomly selecting someone with schizophrenia is 50%. It's even money, right? So the likelihood of a case versus a non-case isn't 2%, it's 50%, right? If we substitute this different prior in here, if we say it's 50%, then the probability of a normal case given a positive test is only about 3%, okay? So these prior probabilities have a big, big impact on what our posterior probabilities are going to be. And so this starts to become important. Remember when we were talking about interpreting Bayes factor bound, as this has been the best case scenario, the absolute highest limit on the likelihood of the alternate versus the null. That's because we're assuming essentially a prior of about 50%, even coin flip stuff. When we actually look at, for psychological science, the actual prior probability, the actual prior, is probably, Laura, can you grab markers that I'll need eventually? Thank you, sorry. I was busy slamming my seltzer water into the ground on the way up. Thanks. 1 to 10, right? And so if we go through and sort of want to translate this into a probability, this is 1 over 10 plus 1. What's 1 over 11? 1, what is it? 0.09 something? 0909. Okay. So really, probably what's reasonable for psychological science is something along this ratio, right? What we do say base factor bound is assuming a prior probability of 1 to 1. And so this is why the argument is we're still giving our data the sort of the benefit of the doubt. We're saying that the alternate and the null are equally likely. And so this is why we're interpreting this as an upper limit on this odds. In fact, probably the actual probability of the alternate relative to the null given the data we have is probably considerably less than that. But again, even at the upper limit, we're still sort of giving us a sort of trying to keep us in check in terms of our interpretations. Okay. Does this help kind of understand what's going on with some of the base factors and thinking about posterior probabilities and or prior probability, posterior probability? And the Bayesian, so this is just kind of an approximation. The Bayesian stuff gets much more complicated than this, and I haven't dug into this because but I want you guys to go through and sort of have an understanding kind of what we're doing and not just spitting out numbers and saying sort of magical incantation words. Okay, cool. And so again, with the S values, with the base factor bound, again, this is something new. This is a new idea that's being kicked around within statistics. Some people like it, some people don't like it. If down the road you decide this isn't something that you want to do, cool, you just get rid of it, right? Or if it comes out that something, sort of someone smarter than me gets way into the sort of nuts and bolts of the math, and they're like, yeah, this doesn't make any sense, cool, we can just forget about it, right? But again, just thinking about with some of the complications of our null hypotheses testing, different ways, looking at different angles, looking at some triangulation on how to understand sort of what our data are telling us and maybe what it's not, to try and start to make reasonable sort of expectations about replicability, sort of the likelihood of the effects that we're talking about, and so on and so forth. Feeling good about this? Okay, cool. So, we had gone through, wave high to the camera, see? All right. So we finished up, we talked about assumptions of our single sample t-test. Assuming continuous outcome, or something that we can at least approximate as continuous. We're assuming our observations are independent. And then our primary concern is with the distribution of sample means. Okay. Tomorrow, if my assumption is the distribution of sample means, am I overly concerned about my observed distribution of scores?
If we're assuming that the population distribution is normal.
Okay, so what does the population distribution have to do with all this?
If the population distribution is normal, then the sample distribution should be relatively normal.
Yeah, so if the population, for which I'm drawing from, if that distribution of scores is relatively normal, distribution of sample means is very quickly going to start to approach normality. Okay, Nick, what's the other condition in which distribution of sample means approaches normality?
When the n is greater than or equal.
When I've got reasonably sized samples, I can have something that's quite skewed in the population, but as long as I have reasonably sized samples, the distribution of sample means starts to get normal very quickly. And so important when we're going through and evaluating scores, some people get hyper-focused and freaked out. They say, particularly for doing means-based tests, they go, my data, my skew and kurtosis weren't exactly zero, so I did a bunch of backflips and transforms and stuff like that. That's a misunderstanding of the underlying assumption. The underlying assumption is what the distribution of sample means. So now if we have small samples, then we might be concerned, right? And if we have a lot of weird outliers, then we might be concerned. But in general, for a single sample t-test, we're just wanting to see that the distribution of sample means for whatever it is that we're looking at are, if we can assume that the distribution of sample means are likely normal, then we're going to be pretty much okay. All right. Questions about sort of basic assumptions of our t-tests? All right. Informal assumptions, we're assuming it doesn't contain outliers, things along those lines, and then all of our auxiliary hypotheses, right? Again, always important to go through and take a look at the methods, and this is extra stat stuff. This is just going through and being a review on our paper and say, is what you've done, does it make sense? Have you done anything strange or weird that's going to unduly bias your outcomes? Okay, so we talked about questions. So we were looking at data from the IEP 32, measure of interpersonal functioning. What we've got is university undergraduates reporting distress associated with prior history of trauma. For the measure, we have normative scores from the larger population of U.S. adults. These are all the characteristics here. This is the characteristics of the sample that I've collected, and what we're going to want to do is we're going to go through and step through and run through sort of different songs and so forth. We've gone through just a recap here. We had run through screening, right? And okay. So if you recall, and again, this is a handout we gave, we went through and ran some screening. Sally, did we have any concerns about sort of the screening of these data?
I don't believe so.
No, we didn't have too many concerns, right? We had to, the biggest thing that we had to do, we had a bunch of cases with missing data, like 70 cases with missing data that we ended up getting rid of. That's a concern, right? We need to account for why we had so much missing data in this sample. But once we got rid of those, and then I believe we had a case that had like a 999 code, probably indicating missing data, although 99 is a reasonable score for this measure. So I want to go through, check the hard copy to make sure that it wasn't sort of a misky, someone just hit an extra 9 to go through. So anytime, again, just in terms of the research, you want to make sure you have hard copy records or originals so you can go through and check on that. But in general, our distribution is looking okay here. Box plot is fairly unremarkable, nothing much going on here. We got kind of someone with a big score, but that's not too much of a concern. We went through, we looked at our standardized scores. Chris, what are we looking at with the standardized scores? Sorry.
For standardized scores, if there are Z scores.
Yeah, and so what are we looking for in the Z scores? What would flag us as maybe something that was problematic?
If there were outliers.
Right, so really high Z scores, things that were very high in the positive direction or very high in the on the low end. Now, having looked at that histogram and the box plot, I already know what I'm going to find here, right? But always good to go through just so that we have another indication of whether or not we have values that are 3, 4, 5 standard deviations away from the mean, above or below, wanting to make sure that we don't have any evidence of weird stuff going on here, okay? So once we go through, again, our big concerns, at least with these data, are going to be addressing, sort of making sure that we had some reason for the missingness that we've observed, and then that one score that was kind of, that was falling out of bounds, make sure that we've accounted for that. But if you go through, you take a look at these screening handouts that you picked up. What we're going to do for the purposes of this class, anytime we're doing a screening of actual data, I've got a framework that I want you to use. Don't get creative. Use this. I tell you that I'm terrified of templates. this is kind of a template. Use this. It also helps me to determine that you understand what's going on with this type of stuff. So this general framework is just kind of an overview of kind of what's happening, so the types of things for our univariate tests that you should probably be looking at. And then I actually went through and wrote up for this example, in-class example, single sample t-test. This is what a write-up for something, or for the example that we've got here. We've got missing values, missing scores for 70 cases. Now, if you've got like 3 or 4 scores, go down and indicate the actual sort of participant numbers. If you've got 70 scores, you don't need to. You can just say 70 scores were missing. Identifying an invalid score, what the actual value was, what case it was. Then sort of telling me that cases with missing plausible values were removed, leaves us with a sample of 334. We've got univariate distributions talking about skew and kurtosis. We're not too concerned about these. This is something I'm going to be a little bit big on. One of the things we'll say sometimes is like, these data were normal, or these data approximated normality. They might, but sometimes we can have things that clearly aren't normal, but still aren't problematic for the purposes of our tests. And so you'll notice my language here indicating, failed to indicate problematic deviations. We're not saying it's perfect, it's not showing us something that would be flagged as problematic. Just giving me a descriptive about the histogram of the box plot, no concerns about univariate outliers, and then just general recommendations, trying to tie this together. It's one thing to say, hey, these data are skewed, or these data violate homogeneity variance, or something along those lines. It's another thing to be thoughtful and think about, okay, like what are the potential complications, right? So like what could actually happen with these data. This set is, we've got a large set, we've got over 300 scores, and everything's lining up about as well as you could hope for actual real data. So we're not too worried about this stuff here, but as we start to get into other stuff, wanting to say, all right, well, I've violated homogeneity variance, what's the likely impact, or I've had sort of this or that, so sort of thinking about that at a little bit deeper level, okay? So, but if we go through, we've gone through our screen, any questions about the screening process? Okay. They'll probably come up, but that's fine. Talk to Laura or I as things start to get a little bit more tricky. So I'm just going to clean this data up. I get rid of all of our one sort of case that doesn't make any sense, and a missing case. And then what you can do is grab the handout that has single sample t-test. Okay. Right here, that's pretty simple. Again, what we've got is instructions on how to get your single sample t, and then the syntax for that. So if we go through and we go to analyze, and we go to compare means, and we go to one sample t-test, we want to look at compare IAP32 score, and what's our test value? What was it, Christy doing?
What the range of scores that are possible?
Not the range of scores. What's the value for this particular problem? What's the value we're comparing against other than null?
0.
Okay, not 0. Okay, because remember what we're doing is we're comparing an independent sample, or sort of a new population, against a known population parameter. And so so this is a very good question. So anybody remember what we're testing this against?
25.
25. Why is that, CJ?
That was what school was for the general population.
For the general population, right? So we've got normative data, and it's not population data, but we'll call it sort of close enough. It's a reference value. We're saying in the general population of adults 18 to elderly, average total score is 25. And our question is do we have evidence that the average score for interpersonal difficulties in a different population, and this different population is trauma-exposed undergraduates, it's a very different population, right? But do we have evidence that, based on the data that we've collected, are we seeing that the average score in this sample is much different than what we would expect just based in the general population? And so based on those normative data, our test statistic here is going to be 25. And then in options, you can just switch around your confidence interval if you wanted to do that. So we'll just leave it at 95. And then I'm going to hit paste. And remember, what you're going to want to do is keep all of this stuff. And again, asterisks will turn anything into comments here. And so you can say, single sample test. Normative mean equals 25. Okay. Again, I can't sort of state enough how important it is that you'll thank yourself. Current you or later you will thank current you for putting these things in here, because right now, and I do this like me right now, says, oh, you'll remember this down the road. I don't remember things 5 minutes from now. So this is super nice. Also, when you're just managing your SPSS data, to the extent that you're putting in labels and things like that, that's also helpful. You'll create variables and then forget why you created them or what they mean, things like that. So just making sure that you get good documentation there. But if we go through, highlight this, run it, the test is pretty easy. Again, this is what I'm saying. The vast majority of your time spent in analysis is going to be screening the data management types of things. Actually running the test is pretty easy and quick. What are we seeing based on these data? What's that?
The scores are different for this sample relative to our, I guess, reference.
Yeah,
sample.
yeah.
The,
And what's causing you to conclude that?
one, looking at the point estimate, which has a mean difference of 14.8. Our sample is above by 14.8.
Yeah.
If we look at our p-value, it's significant, which could potentially indicate that these samples come from different populations, reference populations.
Yeah.
And then the confidence interval provides the plausible difference, amount of difference, which is like the lower bound would be 12, so at least 12.69 points greater on this inventory.
Okay. Perfect. Absolutely fantastic, right? So going through and taking a look at sort of all the evidence, everything that's being communicated here. So we've got, and I'm going to ignore the p-value for the time being, and just looking at the raw difference between the normative population of 25 and what we actually got was close to 40, right? We got almost a 15-point difference. And in a sample of 334, that's really big, right? If we go down through and we take a look, so based on the data that we've collected, we're saying that based on the data that we've obtained, our best guess is that the average IAP score for student survivors of trauma looks to be about 15 points higher than the scores in the general population. But anything from about 12.7 to 17 points higher is going to be consistent or compatible with the data that we've collected, right? So even if we're saying it's a low estimate, our most conservative estimate of 12.7, that's still quite a ways above, right? So just looking at that interval estimate is already giving us sort of pretty clear evidence that, yeah, it looks like and again, remember what we're talking about here is, if this is normative population, and this is trauma survivors, are these means the same? Probably not, right? And so again, our best guess is 39.9. It's looking that these are coming from two distributions that have very, very different means on them, right? And this is basically what our null hypothesis is testing. Our p-value here is saying, giving us the probability of obtaining, assuming that the mean IEP score in student trauma survivors is actually 25. The likelihood of obtaining these data in a sample of 334 is extremely rare. Okay. So one thing, so we won't go through the other thing we can. So if we want to say we want to determine sort of the magnitude of this effect, right? So we say, okay, it seems like quite a bit, right? What can we calculate to determine the magnitude of this effect? An effect size, right? And remember that our effect size for a single sample test is pretty easy. I mean, you can just do a raw difference, and the raw difference is sort of looks like it's big, but IEP units aren't something that's intuitive. So like I can't sort of tell you what the difference between 1 and 2 is like I could in terms of dollars or weight or things along those lines. So what we can do is we can create a standardized effect where we're going to have our mean minus whatever the population mean is over our standard deviation. This ends up being easy, right? Because we only got one standard deviation here. So we've got the difference between our reference value and the sample that we've got, 14.85. And what's my standard deviation for this? What is it? 20.09? Okay. Can someone, so we'll call it, we'll carry it out to 3, 20.09. Someone tell me what my effect size is. 0.739. Okay. All right. Can someone give me a practical or a conceptual interpretation of that effect size? Yeah.
It's like medium effect size approaching.
Okay, so we would say it's medium to, it's starting to creep up on large, so medium to large effect size, okay? What about sort of a real technical, practical interpretation? What are we putting this difference in terms of? Right, relative to, what units is this in? Standard deviation. We can interpret this just like a z-score, right? And so basically, if I'm giving a practical interpretation of this, what I would say is based on the data we've collected, it looks like IEP scores in a population of student trauma survivors is about 3 standard deviations above the mean of what we're seeing in the normal sample, right? 3/4 of a standard deviation, that's a pretty sizable increase, right? And so it falls in this medium to large-ish range, right? Again, we want to, I think Cohen is nice in terms of benchmarks. We want to be a little bit flexible with this stuff. But again, if I found a difference, if this is the type of difference that you're looking for in all of your studies, man, you got a mate in the shade. I don't even know what your research interests are, because we're often not working with this sort of magnitude of effect. All right. Other thing that we can do that we talked about is S values and base factor bound. All right. Now the tricky piece is that SPSS just defaults to tell you like 0.000, right? If we actually go through and we double click on this, so it's 1.8. That's really small, right? So we're sort of 0.0, like 32 zeros before we get to a 1, before we would sort of talk about the p-value, right? And so this is what this is where, when I was talking about sort of reporting p-values in terms of like exponential sort of notation, it's kind of weird, but right here, this p-value could be p equals 0.0004, right? Or it could be p equals 0.00 right out here until we get to 83 or something like that. If we're thinking about p-values as an index of continuous evidence against the null hypothesis, these two things aren't the same, right? Now, I had pretty sweet, I have a pretty sweet Excel calculator that I put up to calculate my S values and my base factor bounds, just because of this reason here. And I'm going to have you guys calculate your own in this next set. You can sort of get a head start on it if you want. Basically, what you can do in Excel is you just put in your T statistic, which is going to be 13.508, and then your degrees of freedom, and then have Excel calculate the actual p-value, and then calculate your S values and your base factor bounds from that. I forgot to upload that here, and I don't want to do a hand calculation with 1.867 times e to the times 10 to the negative 33. But all we've gone through and sort of done this. But so what we would do is we could, in this case, to calculate your S values and your base factor bound for this as well. Questions about the single sample test, how we're going through and interpreting things along those lines. Okay. So, getting back to lecture stuff. Okay. So we're having you go through and do a bunch of things. So one is state the null, say in the sentence, state the null hypotheses, state the null and alternative in statistical notation, 95% confidence interval, index of the absolute magnitude of difference, you were calculating the effect size, conduct your hypothesis test, S value, BFB, and then summarize conclusions and things along these lines. Okay. So here we went through, this is just sort of working through how we request our test statistic in SPSS. Here's our output. In Stata, I don't think any of you probably use Stata. Alicia will. Different interface. It's really nice. So we just t-test IAP total equals 25, and then it dumps all this stuff out. We'll all work with her on that. If you're interested in some other Stata stuff, we can go through and talk about that. But for your assignment, this is me walking through what this assignment write-up might look like if you were to put this all together. Okay. Now, I mean, this is nice. So this is just kind of reiterating kind of what the test was. So, and this is nice to just sort of reorient yourself to what we were actually doing. This is a data screening piece. Actually, don't worry about this. I gave you what I want you to do for data screening. But if you were to kind of write this up, this is kind of what it might look like if it was in words and sort of paragraph form. Actually, having everything in paragraph form is harder for Laura and I to go through and check and see what you did. So we're just having you pulling it out, which is going to be easy for you guys anyway. But here we are going through and we're saying trauma-exposed students evidence a mean of 39.9, standard deviation, suggesting 3/4 of a standard deviation increase in interpersonal difficulties relative to the general population. Okay, so what I've done here is identified what my point estimate is, given a standard deviation, and then given a practical interpretation of the effect size. Population difficulty differences across trauma-exposed students and normative adults, ranging from 12.69 to 17.01, found to be compatible with responses to this study. And so we're saying this is our best estimate, but anything within these bounds would be reasonable. Single sample t-test identified data is highly incompatible with the null model, specifying the population for an average of 25 in trauma-exposed undergraduates. Okay. And here we've got our test statistic, our p-value. Again, I've used exponential notation here just to really drive home, like, this is a really, really small effect. Here's, with my calculator, base factor bound, S values, base factor bounds. So we're going through and interpreting that. I mean, I'm going to have you interpret these two things, but you don't necessarily have to try and incorporate that into your write-up, because basically then every time you're saying, like, these data would be as likely as flipping a fair coin 103 times and it all having, like, we're gonna decide that it's sort of not a fair coin farming time before we hit 103 heads all in a row, right? And basically, functionally, these data are impossible, assuming a population, an actual population mean of 25 from where the population which these students were drawn, right? So I'm comfortable saying that these data are highly incompatible with the null model, okay? Now notice, what I didn't do is I managed to, is it people happy with this? I mean, do people feel like this communicates a reasonable amount of information about sort of the data that we've collected here? Okay. What didn't I do in that interpretation?
You're gonna say like conclusions about the implications of all of that?
Okay, yeah, and so then we're gonna go sort of get down into this, right? Did I say anything was statistically significant or use significant in there? Okay, and so this is one of the things that I mean, it feels like, and I'm still struggling with this too, right? This idea that do we need to label things as statistically significant, not statistically significant? This is a pretty clear-cut case. I mean, I don't have to say significant. I can pretend like it starts to get more difficult as our stuff starts to get more ambiguous. But again, trying to give you all language, and I'm developing this too, how we might talk about this without just giving things an up or down vote, dichotomously saying this is statistically significant, it's not statistically significant, right? And trying to do this in a way that doesn't just sort of get into a semantic issue, right? About, like I'm saying, I just used a code word for statistically significant, right? Basically just saying that the data that we've observed, assume that the null hypotheses are true, these data are incredibly incompatible, sort of based on all the stuff that we've got. These are point estimates, this is lower end, this is higher end, and trying to go through and sort of construct this interpretation in a way that doesn't rely on a dichotomous decision between statistically significant and not. And again, in your own labs, as you go out and doing your own research, if you want to go through and do that, that's perfectly reasonable. I mean, that's the system that we work in, right? But hopefully, we'll think about other ways to think about triangulation, ways to talk about data that don't hinge on statistical significance or not, sort of things along those lines. And then if you want to incorporate data in, then that's easy, right? I think CJ knows what's, when OP is greater than 0.05 or not, and can sort of throw that in if he likes. But again, trying to use some different terminology here, okay? So again, then we're saying results provide support from moderate to large elevations and interpersonal difficulties. While compelling, missing this in the larger set introduces the possibility of response bias, which could influence estimates of interpersonal dysfunction. Again, if I'm just running into these data, I don't know why they're my data. I know why they're missing. If I'm just running into these data, I don't know why we're missing such a huge amount. That could mean we could have systematic bias where everybody who had low values got thrown out, or people who had maybe even higher values got thrown out. I don't know. We would need to go through. It's possible, unless we have are able to account for that, we would need to think, should get more information there. And then here, right? It's important to note that participants in this study were substantially younger, more predominantly female, more highly educated than the respondents included in the community sample. As such, I'm able to determine from this study whether elevations in IP total scores are attributable to or associated with trauma exposure or some other type of factor, right? And again, this is an example of me trying to model, sort of thinking carefully about these data. So yeah, we found a pretty massive effect, right? Overall, this is based on the data that we've collected, it's very clear that whatever population I did pull from doesn't have a mean value of 25, right? But why that might be, I don't know from these data, right? Because the demographics of my sample were very, very different than the population, right? Now the assumption is that people experiencing distress following trauma exposure are experiencing some interpersonal difficulties, and that may be the case. If I had to guess, that's probably what I would think was going on. But based on these data, I can't rule out the possibility that it has to do with age, has to do with education, it has to do with, I mean, on average, if the normative sample was in middle age, and I've got 18, 19-year-olds, our lives are more chaotic in terms of interpersonal stuff at 18, 19 years old, right? It is likely that some of that could be contributing to some of this, right? But again, thinking about the methodology and tying that in and incorporating with our statistics and sort of trying to come up with sort of a reasonable interpretation of stuff. Now, I'm not asking you to be experts in every single thing that we go through and talk about, but sort of based on the information provided, trying to pull some of this together for interpretation stuff. Questions on how I've structured sort of our interpretations here? All right. Now, sort of this, you're not going to get away with this in a journal. That's way too much, right? Particularly for a single sample t-test. Again, if we wanted to translate this into something that you could be more sort of acceptable for journal stuff, here's a much more cut down version. And again, thinking about you guys are learning statistics to publish papers and things along those lines. Like we can go on and talk about, so to spend pages and pages sort of getting fine nuanced interpretations, but at the end of the day, right, particularly who publishes or in their field publishes in like medical oriented journals? Sometimes, yeah. Okay, those will give you back, here's 500 words for an introduction. I wrote a paper, my first author paper was, I had 500 words for the introduction, because it was a medical journal, right? You gotta keep things short and sweet. This would be something that might look like something that's a little bit more pared down. Okay? Wilkinson, that I had Sam Jackson for like a Pulp Fiction shot there. That was kind of aggressive, so maybe just get Mr. T and the stink eye. But again, sort of going back to that Wilkinson paper, like thinking about credibility, generalizability, robustness. Do our results make sense in terms of prior theory, things along these lines? Again, the statistics piece is only a very, very small piece of scientific inference. Want to make sure that you're taking this stuff into account. All right. How are we feeling about single sample tests? Awesome. I'm glad we spent all that time doing single sample tests, because I don't know if I've ever actually published a single sample t-test in my life, but all right. So z-test and d-test are nice because we can go through and compare some sample mean that presumably represents some unique population relative to some known value. But once again, both of these Z and T tests still tend to ask or require more information than we generally have available to us. What is more common is situations where we want to compare means from two or more samples drawn from populations with unknown means and standard deviations. I don't know what the population mean is, I don't know what the population standard deviation is, but I've got this group and I've got this group, and I want to compare these two on some characteristic. This is where we're going to get into our independent samples test. Here, we're looking for differences between two population means. Again, always remember that with our statistical tests, our concern is with the populations. We don't care about the samples. I don't need to do a statistical test to tell me what the sample mean is. I can just calculate it, look at it, and tell you what the sample mean is, right? What we're trying to do is, based on the samples that we've collected, do we have enough information to reason or sort of to conclude that the populations from which these samples were drawn are likely to have different means? Okay, so we're comparing two unknown populations. Population 1, population 2. We don't know what those population parameters are, so we grab samples and test those to try and see if we have enough evidence that suggests, yeah, it's these data would be unlikely to be drawn. These data would be unlikely, assuming that these populations have roughly equivalent population means. Okay. So our null hypotheses for independent sample t-test, mean 1 minus mean 2 is equal to 0. And again, when we're thinking about statistical notation, remember that almost always our test is whether or not some value is equal to 0, right? I could write this as mean 1 equals mean 2, but that actually doesn't quite get at it's statistically what's going on. We're saying that the difference between this is equal to 0. Difference between population means is 0. Scores are likely drawn from populations having equal means. Our alternate hypothesis is actually an infinite number of hypotheses. It's just saying that sort of whatever these two population means are, there's some non-zero value. They're not the same, right? Our test, what we're hoping to conclude is that our sample score is unlikely to have occurred if the respective population means were equal. So again, our question here with our independent sample test is, do we have enough evidence to start to conclude that these samples were drawn from populations having different means? All right. So, I jumped right into assumptions. I didn't know I jumped right into assumptions right away. I was confused. All right, so formal assumptions of our data. Someone tell me, why are we concerned about, Christy, why do we care about assumptions?
Just in general, or for independent samples t-test?
Just in general.
Because a lot of the tests we run are based on assumptions that the data, or about the data, and if those are violated, then we can't conclude anything from them.
Okay, and so you're right on the right track, right? So the concern is sort of mathematically, if these data meet certain specifications, these things are true about sort of data, or we can infer certain probabilities of likelihood or not likelihood of observing stuff, right? Again, our statistical models are based on mathematical theory that assume sort of perfect adherence to sort of the underlying assumptions. The problem is, if we start to violate those assumptions, now all of a sudden that mathematical model breaks down. I start becoming less confident that those probability values that I've calculated actually are the probability values that should be taking place. Now, the thing to remember, particularly for our independent sample tests or means-based tests, these tend to, based on simulation work and sort of other stuff, tend to be pretty robust, right? So we can start to have some violations of sort of homogeneity of variance and some of the data stuff, and the tests tend to be pretty still. They're not perfect, but they get us pretty close. Now, if we start violating underlying methodological stuff, I start to have biased samples, or I've got a bunch of different people are doing different things, there's different sorts of bias and stuff like that, then all of our inference goes straight out the window. We can't infer, we can't correct for that. But what we want to do is make sure that at least our data are sort of reasonably close, so that I could, with a straight face, stand in front of Cynthia and say, yes, these data aren't perfect, but I think they're good enough to allow us to sort of make these basic inferences. So for our independent sample t-test, we're assuming that our outcome variable is continuous. That's important. And we're assuming that our observations in each sample are independent of one another. That means people in this group and people in this group, there's no connection between their scores. Their scores are completely independent, completely uncorrelated. We're assuming the distribution of sample means for each population is normal, right? So again, this is all stuff that we've gone through before. But then with our independent sample test, we also have the assumption of homogeneity of variance, right? What we're assuming is that the variance in both populations is equal, okay? So what I don't want is a situation where my population variance, pop 1, here's my mean, and my standard deviation is that, and then in this sample, here's mean 2, and the standard deviation is whatever that is times 8, right? So the spread here is way larger than the spread here, okay? So what we want to do is we need to go through and do some extra tests to try and see, is based on the data that we've collected, do we have evidence that at least the likely variance parameters across these two populations are relatively equal. If they are, awesome. If they're not, there's some things that we need to go through and correct and change up a bit. Okay. We'll get into this, but people sort of understand this homogeneity of variance assumption.
similar.
Yeah.
They don't have to be like the same.
They don't have to be the same.
Okay.
And again, we probably couldn't test sort of enough so they would be exactly the same. But this starts to be, if I get a large enough sample, am I going to find that they're different?
Hopefully not.
If I get a really big sample, what happens to the sample of our test, or what happens to the power of our test as our samples start to get really, really big?
It increases.
Right. And so even sort of minor deviations can start to come up as statistically significant. And so this is why we have to be careful. So if I've got one sample of 500 and another sample of 600, and I see that if I violated homogeneity of variance, first thing I probably want to do is take a look at what those actual variance estimates are. Because if objectively they're really close to one another, I probably just have too powerful of a test, right? I don't need to worry too much about things, right? So these are the types of things where we have to, it's important to understand what's going on with these tests so that we can make proper interpretations and not sort of scream the sky is falling when it's not. It's just, basically what you're saying is actually what should happen given the data that you've got. So, but in general, sort of other thing too, right? Like we'll see in an example, we fail to reject we don't find evidence of differences, but we've got a sample of 5 and 20. We don't have a lot of power in that test to really say whether or not we have a difference there, right? So wanted to take some of this stuff into consideration. So again, homogeneity of variance, data don't collect outliers. Informally, we're expecting equal sample sizes across groups. Now we can tolerate some differences in cell sizes, right? But if we start to get things that are super, super discrepant, then we start to run into problems, right? So this is what happens a lot of times. If we're interested in racial ethnic things, right? I've got 10 people in this group and 250 in this group. There's not much we can do with that type of stuff. Now we can deal with unequal sample sizes. It sort of reduces the power of our test. And sort of when we start combining it with other stuff, there's bad stuff that happens. But if it gets too big, then what we've got is basically a univariate outlier in terms of our grouping variable or 0-1 stuff. Okay. So we're assuming relatively equal sample sizes, and then including that all our auxiliary hypotheses that sort of aren't part of our statistical analysis. This is just a post-methodological read. Okay. All right. Why don't we take a break, and we'll jump back in on our return. Try not to be too amazed. But, so the nice thing is here, right? So if I'm calculating, so with this example, our t-test was 13.508. That's crazy. With 333 degrees of freedom, right? SPSS is just going to give me 0, 0, 0, zeros into infinity, right? To try and calculate that by hand is going to be a pain unless you're sort of down. You got your HP graphing calculator here. Excel will do it pretty easily and straightforward for you. All you need to do is, and here you just put in the t-test, 2 degrees of freedom, and then I just have it calculating my PS, the base factor bound, and then the posteriors and the probability is 0. Also, if I want to go through and just punch in a p-value, I can do that too if I'm not working with something that's a t-statistic or something along those lines. We're going to be doing a lot of these over the course of the semester. These are just nice tools to have on hand. It just automates what you're doing so you don't have to crank out log base 2 of 7,000 different things. So. All right, let me get back to independent sample t-test. Questions about anything up to this point? Okay. So for our independent sample test, what we're looking at is our test statistic, right? And our t-statistic, this is what we're talking about with our t-distribution. This is the distribution of our test statistics, assuming the null hypotheses, right? So we've got mean 1 minus mean 2, subtracting null 1 minus null 2, okay? But because we're assuming under our almost sort of the way we're typically running things, we don't have to run it this way, but we do run it this way. We've got a standard error estimate, right? This is the standard error of the difference in means, and this gets a little bit tricky, okay? So here we've got the standard error of the difference in sample means, and what this is thinking about, or sort of conceptually what's going on here, this is the expected difference in means across samples, assuming the null hypothesis is true, okay? So if this population and this population had equal means and equal variances, and we were to repeatedly calculate, draw a sample of 50 from here, a sample from 50 here, and take the difference in those means, overall, how much would I expect, over an infinite number of replications, how much would I expect the difference in those sample means to jump around, right? Sometimes the differences are, sometimes we're going to get a really big difference, sometimes we're going to get a really small difference, but on average, they're going to fall right around the middle. Our standard error, just like we've always talked about, is just an estimate of precision. It's telling us how well we're expecting these sample statistics we have to represent the actual population parameter. So we've got a really big standard error. That means our test statistic is not precise, right? We're expecting across repeated replications this difference score, we're expecting this to jump around a whole lot. As our sample size starts to increase, as our cell sizes get larger and larger, that standard error is going to decrease, and so it's going to move around a lot less, right? Now, when we're thinking about our independent sample t-test, we've got two sources of error with our independent sample test. Before we just had the one, we were just working with the one sample. But now with our independent sample t-test, we've got two sources of error. We've got our mean one, right, from this, getting rid of this, assuming these are the same. Okay. So we know that when we go through and we sample from population 1, our sample is going to estimate the mean of population 1 with some error. And then I'm going to go through and I'm going to draw a sample from population 2. Sample 2 is going to represent the mean of population 2 with some error. And as a consequence of this, we've got error coming from both of our samples, and we need to go through and take that into account when we're going through and calculating our test statistic. Okay? And so what we do to get the standard error of the difference in means is we're going to take the square root of my sample variance over the sample size of sample 1 plus the sample variance of sample 2 over the sample size of my second sample here. Okay? So the idea is that unlike standard error for our single sample test, and from our Z's, where standard error was just square root over the sample size, I've got two sources of error. And so what is this going to do to my standard error in my independent sample test relative to my single sample test? It's going to make it bigger, okay? We've got more error. It's going to make my standard error larger, and if my standard error is larger, then what does this do to my test statistic? It deflates it, makes it smaller, right? And it brings it down, right? And so we're thinking about what's going on with this, right? If we think about the variability in our different set of scores, we've got two populations here. We've got population 1 and we've got population 2, right? And so we want to know possible range of two randomly selected scores from population 1 and population 2, okay? At one extreme, we could pull from population 1 a score of 95 and a score of population 2 so population 2 pull a score of 95, where is it? 2 and where's 15? Oh, okay, yeah, got it here. All right, so population 1 have a max of 95 and population 2 range of 15. So that's one max or one extreme that we could get. We could also get an extreme of 65 in population 2 and a score of, a score of 25 in population 1 and 65 in population 2. So there's two different extremes. In the first extreme, I get an estimate that says population 1 is 80 points greater than population 2. In the second extreme, I get a score that says population 1 is 40 points smaller than population 2. Those are the two possible extremes that I could get for these scores. And if I plot this out on the number line, between negative 40 to 80 is a 120 point difference, right? So I'm taking error into account for both of these. Consequently, if I add the ranges of those two populations together, I get the same difference here, right? So I could, based on any just single scores that I pull from these two populations, I get very different conflicting results. At most, I say population 1 is 80 points higher than population 2, or I say population 2 is 40 points higher than population 1. As we going through accounting for the standard error, we need to make sure that we're accounting for all possible sources of error in this. And so what ends up happening is our standard error, the difference, ends up being an additive function based on the variability within each one of these populations. So again, we've got variance of sample 1 over the sample size, plus the variance of 2 over the sample size. All of that taken to the square of that is going to give us our standard error. People seeing how we're adding in, so why we have to take into account multiple sources of error. We've got two samples that we're testing, both with their own independent sources of error. All right. So, but what happens if our samples are different sizes? We say an informal test, or an informal assumption of our tests, is that our samples have roughly equal sizes, right? But what if they're not, right? A lot of times when we're doing applied research, it's just not possible to get equal sample sizes, right? And so what happens if I have one sample, I have a sample of 10, other sample, I have a sample of 30, okay? Well, this starts to become problematic because we know that larger samples give us better estimates than do smaller samples. So now I've got two estimates of the population variance, which I'm assuming is the same, because that's an underlying assumption of the test. But we know that the larger sample is going to give me a better estimate on average of population variance than the smaller estimate, or than the smaller sample. Okay. So again, our homogeneity variance assumption says that we're assuming that the variance of this and the variance of that is going to be equal, right? But with our independent sample t-test, our estimates of our estimates of our population variance are never going to be the same. They're always going to be a little bit different, right? So even if they do, even if we haven't violated homogeneity variance, my sample variance for this sample and my sample variance for that sample aren't going to be the same, right? They're going to differ by at least some, all the way up to maybe quite a bit, right? And we need to know how to address that issue. And so in cases with our unequal sample size, our concern is that if we just weighted them equally, the smaller sample is going to exert an unwanted influence on the estimate of the population, right? So let's say that I've got, in my smaller sample, this is my sample of 10, and I get a variance of 20, and here, my larger sample, which should be a better estimate, I get a population variance, or I get a sample variance of 8, okay? If I just add those together, my estimate of the population variance, even assuming that these two things are going to be true, is going to be, so what, 28 divided by 2, 14, right? Which is considerably larger than sort of the estimate I had for the better sample, right? So what we're going to do is we're going to go through and we're going to pool our estimates, okay? And what we're going to do is we're pooling our variance estimate based on the size of the sample, okay? So here, and just to go back, so if we just were to go through and average the two of them and treat them as though they were both equally precise estimates, what we would end up is the case with the sample with the smaller estimate is always going to have more influence on our population estimate, right? If we just average them up. And so if my sample variance in my smaller sample is lower, it's going to make my population variance look a lot smaller. And if it's a lot bigger, it's going to make it look a lot bigger. And so what we're going to do is we're going to pool that variance. Pooled variance is just a weighted average of your sample variances, pretty straightforward. We've got our degrees of freedom, n-1 for sample 1, multiplied by the sample variance, plus the degrees of freedom for sample 2, multiplied by the sample variance, all over the total degrees of freedom for our test, which is the sample size of sample 1 plus sample 2 minus 2, because we're estimating 2 variances, so we lost 2 degrees of freedom here. Okay. People see what we're doing with the with our pool variance estimate here. Okay. So again, we're just weighting this to give more weight to the larger sample size, because we're assuming that it's got a better estimate, giving a more precise estimate of the population variance. So our final formula for our independent sample t-test is we've got mean 1 minus mean 2 over subtracting sort of whatever our hypothesized difference is. That's going to be 0, that cancels out, over our standard error. Our standard error of the mean is going to be our pooled population, or our pooled sample variance over the size of sample 1, plus the pooled variance over sample 2, right? Take the square root of that, and that's going to give us our t-statistic. Our degrees of freedom are going to be the size of sample 1 plus sample 2 minus 2, because we're estimating 2 variances within this whole shindig here, and so we lose 2 degrees of freedom based on this stuff.
So do you do this even if you have similar sample sizes?
So mathematically, do I need to, if I've got equal sample size, I got samples of 50 in both cases, right? And I calculate my pooled variance, and then I just take the average of the 2 variances. Which one of those is going to be higher?
The one with less people.
I tricked you. They have equal sample.
Okay.
It's going to be the same number.
That's what I was thinking.
Yeah. See, there you fell for it. Yeah, I just laid that trap out. You walked right in. They're going to be the same, right? And so if you have equal samples, you can just sort of take variance 1, variance 2, and divide by 2 and average it. It's going to be the same thing, right? Now the thing is a lot of people will sometimes get confused, and if you just always use the pooled variance, it's a fail-safe, right? It's going to be sort of more steps, but whatever you want to do is fine, right? Just wanting to know kind of what's going on with this. But if you run into a situation where you've got a perfectly balanced test, and this actually doesn't happen a whole lot, but if it does, you can just say sample variance 1, sample variance 2, add the 2, divide them, and that's going to give you the exact same thing as pool variance. All right, so yeah, when you're calculating your standard error, this pooled variance estimate is going to be the same. So it's just going to be some number over the size of the number of people in sample 1 plus some number over sample 2. Okay. Other thing too, remember when you're calculating your standard error, you're using this. These are variance estimates, not standard deviations. Put standard deviations in there, that's going to screw this up. It's going to make things look way smaller than it should be. So just making sure you're careful with your notation there. All right. Degrees of freedom. We don't pay attention to degrees of freedom a whole lot. Why is it important to know degrees of freedom in your analyses?
Because then you understand the amount of plausible values.
Yeah.
You're at.
The reason I think it's super important, testing these solve goddamn mystery, trying to figure out what the hell someone's doing in their study, is looking at that degrees of freedom, right? Because what happens if someone's running a bunch of t-tests, that degree of freedom starts jumping around, what does that tell me about their samples?
They're including and excluding certain.
Yeah, there's different people going on, right? And if you told me, I'm missing these people here, and missing these people here, and sort of this, and I've decided to go through and do, I don't care for that approach because it's hard to sort of compare directly. My preference would be you just take the people we got all the data for and just that's your inclusion sample. But different reasons why you might not do that, right? But if I'm going through and I'm looking at statistical tests, I'm seeing that degrees of freedom start jumping around, I know it tells me something about what's going on in the background methodology that maybe hasn't been reported in the or sort of somewhere, been made explicit in the paper, and it lets me know, particularly if it's jumping around a whole lot, like, hey, you're looking at very different samples across this, and so these analyses might not all be comparable. Okay, so I'm gonna do some Scooby-Doo stuff, right? mystery, right? You get ghosts, right? Paranormal distributions, yikes. I was gonna pull that out, but then I didn't because it made me laugh, and so not sure with that one. All right, thinking about effect size. All right, as we start thinking about standardized effects, things start to get more complicated when we get into our independent sample t-tests. Okay, our benchmarks, our performance benchmarks for our effect sizes are going to be the same, right? 0.2, generally small, medium 0.5, large about 0.8, right? But if we're thinking about with our independent sample t-test, we can still use raw difference as a measure of meaningful effect. If, again, I'm working on using reasonable or sort of interpretable units, right? If I'm looking at pay discrepancy among male and female professionals, right? And I see the pay gap is $8,000 for people doing the exact same thing. I know what that means, right? I know quantity-wise what $8,000 is, and or if it's $500. That's a meaningful thing. I can say, well, it's a lot or it's a little, things along those lines. Problem is, a lot of times we're not using effects or metrics that have intrinsic meaning, and so we can fall back on our Cohen's d. Now, Cohen's d for independent sample t-test is just mean 1 minus mean 2 over standard deviation. Okay, what's the complication with this estimate of effect? What do you think, Chris? If I had you just, if I said calculate me a Cohen's d for an independent sample t-test, what question might you have for me?
Which standard deviation?
Exactly. Which standard deviation do I use? Okay. Now Cohen would say it doesn't matter, right? Because we're assuming that these populations have equal variance, so it doesn't matter which standard deviation you use, right? Which is true from a theory-based standpoint, but from a practical standpoint, which sample standard deviation might I be tempted to use?
Smaller.
The smaller one. Why?
Because it will increase your.
It's going to make my effect size look bigger, right? This is maybe too much pressure on me to try and determine sort of which one that we can use. And so we have different sort of approaches to how we might think about this. Glasses delta, this is a classic effect size statistic. And with glasses, what we're doing is we're going to take a look at the difference in means, and we're just going to divide this into the standard deviation we're going to use is for some control group. Okay. A lot of times, let's say CJ, you're running a manipulation on something, and you've got people coming in who are just sort of not doing anything. They have some sort of neutral priming condition or something. There's just nothing going on. It's just sort of people, right? And then your comparison condition is an experimental group where people are coming in where you're actually doing something that you're hoping is going to change stuff, right? In this situation, if you're looking at mean differences between these two groups on some outcome, glasses delta might be, it's probably going to be a nice option for you to use, because what we can do is we can talk about things in terms of standard deviation relative to baseline, or standard deviation relative to control. So relative to not doing anything, we're seeing that the experimental group is falling half a standard deviation or above or half a standard deviation below in terms of standard deviation units, sort of relative to what we would normally expect. Okay. Or this is also a nice option for intervention research. So because let's say you and Kyle's lab are doing like a weight, some sort of weight intervention or something like that. You've got a normal control group where people are just have normal body mass and or things along those lines, right? And then you've got a group that are sort of trying to do something, right? Well, here, and particularly with something like a physical property, like people are probably like the standard variability of people's sort of mass or something like that is going to be pretty standard, right? So we know. And so then if I say what we found in this treatment group is we've seen a full standard deviation increase in or decrease in weight or increase in weight relative to variability at baseline or relative to variability in the normative controls, that has intrinsic meaning, right? Because that metric, like, well, I know about what the standard deviation is, and so then that starts to become an attractive metric to use, right? And so then what we do is we just use the base standard deviation of our baseline or our control group. But sometimes we don't have a clear control group, right? Sometimes we've got a group that, so both of them are kind of, right, CJ, you're doing it, you're writing, so this group gets this manipulation and this group gets this manipulation. Which one do we say is the control? So like, which one is the control group? Well, they're both to their own unique thing. This is where we get into effect sizes known as hedges G. And what we do here is we just take the difference in means and we just divide it by the pooled standard deviation. So our pooled variance estimate that we calculated for our independent sample t-test, we just take the square root of the pooled variance and use that as my standard deviation. And this is just the weighted average standard deviation across my two groups. It's sort of our compromise, right? And this can be a nice, and this is, when you hear anybody reporting Cohen's D, this is probably what they're reporting right here. The other thing that happens though with our hedges G is we know that effect sizes, small samples inflate effect size. If I've got running a test where I've got a sample of 10 and a sample of 8, right? And this is where when we talk about problems with sort of replication crises and some of these experiments that we ran in like the 60s and 70s and 80s that no one else can get to replicate, a lot of these are based on really small sample studies. And what we know when we're working with these small sample studies, we get our estimates of our effect size. Because effect size, our sample, or the effect size that we get for our sample or for our test is an estimate of the larger population value, right? And we know that if we have small samples inflate the effect size. It makes it look bigger than it actually is. And then we're all out searching for an effect size of about 0.5 based on the sample of the study of comparing 10 people and 8 people, when in actual fact the effect size we're looking for about 0.2 or 0.15 or something like that. And then we're confused as to why we can't replicate things, right? And so what we can do is a proposed correction for G. So we talk about this as hedges and bias G. What we do is you take your effect size that you calculated here, and then just impose a correction. Okay. So again, you're not correcting for glasses. This is just for hedges, right? You take the effect size that you calculated, and then multiply that by 1 minus 3 over 4 times sample size. So basically your degrees of freedom minus 1 for all that. And what this is going to do is it's going to go through and it's going to create a correction for your hedges G. Okay. So what's going to happen to that correction tomorrow as your sample sizes start to get larger? As your sample size gets bigger and bigger and bigger, what happens to the correction to your hedges G? Okay. So let's say if we take 3 divided by, and let's say it's 18 degrees of freedom, right? Versus 3 divided by this times 100 degrees of freedom. What's going to happen to the actual correction factor? It's going to get smaller, right? And so again, this makes some sense. We want a correction factor to get smaller as our sample size increases. As our degrees of freedom, as our sample gets bigger and bigger and bigger, we're assuming that this is getting less and less bias, right? So as our sample sizes get bigger and bigger and bigger, this correction sort of reduces to something that's functionally negligent, right? But if we have very, very small samples, this correction is going to be a downward correction on your G that ends up sort of being more severe than if you have larger samples.
Is the hedges unbiased only applied to the hedges G though? Or
Yep.
does it apply to any of the others?
No, just stick with this. These two
Okay.
things together. Yep. Don't try and correct glasses delta or anything like that. Okay. But if you're working with really, really small samples, maybe you'd say, well, I could use glasses delta. I've got a real baseline, like a good control that might be useful, but I'm working with really small samples, so I'm just going to use hedges unbiased G anyway.
Are we talking about like less than 30?
Yeah, ish. You know. I mean, what did you say?
I said I was just talking about practice, which is an Allen Iverson quote.
Oh. I would ask you to explain it, but that would make me feel foolish. So
I'll show you the after class.
Okay. Yeah, probably. I mean, if you're, and again, so this is based on 12 degrees of freedom in your test. If you've got, 30 degrees of freedom, you've got 16 people in each group. That's still pretty small as it starts to go up. And you'll see, I mean, You don't see this a whole lot. This is kind of like an adjusted R squared. You don't see adjusted R squares a lot in our field. You see it much more in other fields. So it's kind of a thing. But and it's might be worth sort of looking at, sort of seeing how much over perfection you get there. I mean, it's all going to be pretty close. So I mean, we're talking about differences based on the hundredths position. But so it doesn't make a huge difference if I say my effect size is 0.48 versus 0.43. Probably not, but so something to be aware of. All right. Other thing we can do is we can start to, with an independent sample t-test, we can start to calculate effect sizes based on secondary analyses. If you have your own data, do not do this. This is kind of ends up being an approximation. If you have access to your own means and standard deviations, just do this, right? But if I'm reading Siley's paper and Siley doesn't calculate any effect sizes, I'm like, Siley. And what you do have, if you've gone through and you reported t-statistics and degrees of freedom, I can go through based on those test statistics and get an estimate of effect sizes. Sort of here, I can do this, sort of go through and get an approximation of that effect based on the t-statistic that you've given me. Questions about effect size, any of this stuff? Okay, cool. So, I'm going to run through an example. So we've got back to interested in school stuff. Okay, so we've got researchers are interested in school performance in students having watched Sesame Street as children and those who did not. Scholastic performance in 10 high school students having viewed Sesame Street in childhood compared with 10 students who have not. Students having watched the program had a mean grade of 93, the variance of 22.2, while those with no exposure had a mean grade of 85, variance of 17.8. So again, we're going to go through null and alternative using, say the null and words, statistical notification, 95% confidence interval, index of absolute magnitude of effect, hypotheses test, S value, EFB, and summarized conclusions here. All right. Let's go through and just calculate our basic stats here. So first thing I'm going to do is calculate a 95% confidence interval. So I've got sample size 1 is 10, mean is 93, variance is 22.2, and I've got sample size 2 is no Sesame Street, mean is 85, and variance 17.8. Okay. What do I need to do? What's the first thing I need to do if I want to calculate a confidence interval? Christy?
Change the variance to standard deviation.
Okay. I could.
Oh wait, I guess you don't have to.
Yeah, I don't need to do that quite yet. What do I want to do?
You want the standard error.
Standard error, right? Okay. Now, do I need to calculate the pooled standard error?
No.
No, there we go.
Same size.
Right, they're the same size, right? So like, yeah, lay that same trade you're learning. That's awesome. No, we don't. I'm going to go through and do it just to sort of illustrate how you would do it, but you wouldn't need to. But let's say that we are, and so I'm going to calculate my pooled variance, and so I'm going to take 10 minus 1 times 22.2 plus 10 minus 1 times 17.8 all over 10 plus 10 minus 2. So tell me what we get in terms of pool variance estimate. this one works out into actual numbers. Okay, so that's my pooled estimate. What if I take 22.2 plus 17.8 divided by 2? What do I get? 20. 20. Right. So if you don't need to, this is a shortcut, but in general, most of the time when we're working with real data, we often won't have perfectly balanced sets. So, all right, so this is our pooled standard deviation. So now I can calculate my standard error. Standard error is going to be the square root of 20 over 10 plus 20 over 10. It's giving me a standard error of what? 2. What is that?
2 plus 2 is 4.
Oh, yeah.
4 is 2.
There you go. 2. Good work. So standard error of 2. Okay. So I want to go through 95% confidence interval. Is going to be my point estimate of the difference. What's the difference in my scores here? 8. 8 plus or minus. What's my T statistic that I'm going to use here? So what's my degrees of freedom?
For your pooled degrees of freedom?
Yep, it's going to be to my pool degrees. 18. Right? So 10 plus 10 minus 2, so 18. So 95% confidence interval for a two-tailed test with 18 degrees of freedom. So I'm going to have there. Is it 2.101? 18 degrees of freedom. Just like it. 2.101. 2.101 times 2. What's my interval that I get here?
The upper bound is 12.202.
12.20 lower bound.
3.79.
3.78.
979.
79. Is that what people got? Cheap. We'll do 3.8. Okay, yeah, close enough. All right, cool. So, Say, can you give me an interpretation of this confidence interval here?
It's fairly small.
Okay, well, so what are we thinking about? We're talking about, and this is where it starts to become important, right? We want to be thinking about our determination on whether or not something's large or small is going to be determined on the units, right? And so our units are kind of ambiguous, but we're saying mean grade. So I don't know exactly what mean grade on what, but it's mean grade. So we've got anywhere from about a 4-point difference in grade to a 12-point difference. So that's kind of big, right? And again, if we sort of look at our sample sizes, these are pretty small, right? And so we're talking anywhere from just under a half a grade difference between these two groups, all the way up to over a full grade point difference, right? So kind of a decent size range on this, right? But in general, it's looking like my students who have been exposed to Sesame Street have about an 8-point higher overall grade than students who average than students who don't. What do I conclude about sort of that in terms of magnitude of effect? What do you think, yeah?
I don't know if this has been said, but we can extract the difference between the two groups, the individuals having watched Sesame Street to have at the lower bound a 4-point greater score and at the upper bound a 12-point greater score.
Yeah, exactly, right? And so again, if we're thinking about this in terms of average grade, that's actually, I would argue, not a trivial amount, right? A 4-point, anywhere from like about a 4-point difference to a 12-point difference in grade points. We're kind of working with a restricted range. I mean, that seems fairly substantial. right? So even though this is quite a wide interval, even the lower bound, if I say, hey, you have a 4-point difference in terms of your grade, that's a difference between like an 87 and a sort of 90, right? In terms of things. So I would, if we're trying to think about like what these units actually mean, which we always should, it seems like a non-trivial difference, at least based on the data that we've got here. Okay. So we calculated our confidence interval. What should we be thinking about in terms of an effect size?
Hedges unbiased.
You think hedges on? Chris, tell me why you like hedges unbiased.
We have a small sample size, so the effect size might be extremely high.
Okay.
If we do coincide.
Okay.
Well, we want it to look cool when we try to publish it. So.
Right. Well, that's the thing, right? Okay. So we go through, but I think you're right? I mean, I think we could say that we could talk about maybe this students who are not exposed to Sesame Street as a baseline, right? This is what happens in terms of variability, in terms of kids that just don't have access to educational programming. But given the small sample size, I think hedges unbiased is probably a better estimate, right? So if we go through and our difference is 8 over our pooled variance, or our pooled standard deviation was, our pooled variance was 20, right? Yeah. And what, so what's the square root of 20?
4.47.
4.47 what?
4.472.
Okay. We carried it out to 3 just for our calculations, so we're all together. So someone tell me what my hedges G is here. 1.789. That's pretty impressive, right, in terms of a mean-based difference. But we know that with small samples, this is probably an overestimate of the population value, right? So if we're going to calculate hedges unbiased, we've got 1.789 times 1 minus 3 over 4 times 10 plus 10 minus 2 minus 1. What do we get for our correction factor here? You get it? It's not with a 18. You got it tomorrow? Yeah.
So it's 1 minus 3 divided by 71.
1 minus 3 divided by 71, yeah. What is the actual, what is my number here, my correction factor? You got it there. Tell me what it is tomorrow. 0.958. Okay. So we're seeing correction. Anytime we multiply anything by a decimal, what happens to that number? It's smaller, right? And so we have a little bit of a correction here. And so what does my hedges G, my unbiased G end up being? Today, 1.789 times 0.958.
0.924.
What is it?
0.924.
0.924.
I have 1.7.
Yeah, I think that's too much of a correction there. What did you get?
1.714.
1.714. Okay, that makes more sense. So it's going to be, it should be close to sort of what we've got. Let me see what I calculated. For unbiased, yeah, 1.71 is what I ended up with. Okay, so we see we've got our estimate. We've got our unbiased G, or we've got our estimate of our effect size, and then we're just making a correction for this small sample, and it takes it down to 1.79 to 1.71. So again, we're generally talking about issues in terms of like a tenth of a, or in the hundredths place, but it's smaller. It's probably a more accurate estimate of the population value. That based on the data that we have available to us, it looks like children or adolescents who were formerly exposed to educational programming are scoring in terms of their average grade about 1.7 standard deviations above those not exposed to education. We're getting close to 2 standard deviations above, right? Like this is a small sample, but this is still starting to be fairly compelling, right? All right, we want to conduct our hypotheses test. That's pretty straightforward. So we've got t equals difference in mean 1 over mean 2 is going to be 8 divided by our standard error was 2. Going to give me t value of 4, right? Am I going to reject the null hypothesis with a t statistic of 4? Yeah, that's huge, right? If I want to go through and I want to calculate an S value and a t value, or an S value and a base factor bound with this, I say 4 degrees of freedom, or a test statistic of 4 with 8 degrees, or 18 degrees of freedom. 18 degrees of freedom, S value of 10, right? Remember, because we round that to the whole, and our base factor bound saying database odds of our alternate being true relative to the null is at most 61.8 to 1, right? This is pretty big. Other stuff you can see, so we've got upper bound probability for the alternative relative to the null based on the best case scenario is about 98% chance of the alternate relative to the null. In the best case scenario, about 2% likelihood that the null is actually true based on some of these statistics, right? And so again, this is just based on, so you're calculating all this based on the null hypothesis here. So my p-value, 0.0008. And so once again, if I'm thinking about my p-value as an index of continuous evidence against the null hypotheses, I would say that it's fairly compelling evidence against the null hypotheses, assuming that sort of my data and all relevant assumptions that I've got representative populations that I don't have anything screwy going on my data, things along those lines, is all, this is, we can take this as fairly compelling data against the point null. So, gone through and done through, worked through all of this, okay? We wanted to take a look at just summarize results. Statement of the null, mean grade of high school students exposed to Sesame Street and high school students not exposed to Sesame Street is equal across their respective populations. Again, making sure in the statement of the null hypothesis that you're letting me know so that I know that you know we're not talking about samples, we're talking about populations, right? So making sure to incorporate that in. Null and alternate hypotheses here, confidence interval, here's your various different effect sizes that you could have put together, but I agree, I think unbiased G is probably the best for this. Our T critical, 2.101, our actual T was 4, p-value, if we wanted to put this in notation here, we could do that, right? S value, okay? And again, I'm going to have you report S values, but this is kind of a hard interpret S values, but I'm pretty much just going to have you interpret them just here. Again, as I've said before, I think if I was envisioning how to incorporate this in actual research, I would just have it in a data analytics section of my methods, S values, and how they're interpreted, because I don't know how many other ways you can say this without it sounding weird and confusing, but results of the independent sample t-test provide similar evidence against equivalent performance of these populations as would observing 10 successively heads in tosses of a hypothesized fair coin. I played around with this a lot to try and sort of communicate what this is, if I try to play around with this a lot, it's going to start making not a lot of sense. And so it starts to feel a lot like cut and paste stuff, and that's going to get redundant if you start incorporating that into all of your methods. I think sort of indicating early on, if you were to ever use this in a publication, just in the analytics section, S values, this is what they are, this is how you interpret them, and then after that, just sort of reporting them in the thing. We've got base factor bound 61.8. Based on the available data, the likelihood of greater academic performance among Sesame Street exposed high school students versus non-Sesame Street exposed students is at most 61 times that of equal academic performance. Right? So we're talking about the likelihood or the odds of the alternate hypotheses relative to the null. And then trying to tie this all together, saying students reporting exposure to Sesame Street in childhood demonstrated an 8-point increase in average grades compared to high school students with no prior exposure. Difference in these data is consistent with a 1.7 standard deviation increase in performance relative to students with no Sesame Street exposure. Estimates of population difference compatible with these data range from 3.8 to 12.2, right? So again, just going through and sort of talking about sort of the magnitude of the effects that we're seeing. Say despite the small sample available for the study, results of the independent sample t-test provide relatively strong evidence of greater academic performance in students exposed to Sesame Street in childhood. Here to report our test values, our P, our S, our BFB. We're just saying that it's pretty compelling evidence if you want to sort of make inferences about traditional rules of statistical significance, things along those lines. They're free to do that based on sort of what we've provided. We say although the methodology of the study requires additional scrutiny, current data suggests early exposure to education programming could be associated with 2/5 to over a full letter grade increase in average exam scores, right? So I'm kind of looking at that level here, right? So again, trying to say not only is it different, but how much is it different? Even the lower bound, I can tell you if I told my intro students, I'd be like, hey, I'll give you a 4-point bump on your overall average, no one's going to turn that down as nonsense, right? They'll write papers for what, like, I mean, again, that's a pretty big jump in things, right? So again, not wanting to, large samples are good, and large samples generally give us some more precise estimates about what's going on, but assuming that we have good methods, even research that's using relatively small samples, assuming that the methods are strong, can provide some reasonably compelling stuff for sort of evidence for outcomes, right? So again, based on sort of the class that I hung out in Kyle's class with you all that day, talking about you working through single subject methodologies, right? It's like you can't have a smaller sample than one person, right? But if you do those designs correctly, I can provide incredibly compelling evidence for sort of effects and things along those lines. So not everything has to be massive large samples. That's nice if you can get them, but if you can't, focusing more on methodology and then reasonable interpretations of your outcomes. Questions on any of this? Yeah.
Why is the null and alternate 20?
What's that?
Why is the null and alternate equal or not equal to 20?
It's a good question. It shouldn't be. It should be equal to 0, right?
I thought
yeah.
I was following it, and that's not that.
Yeah, no, nice work. Laura, can you send me an email to fix that? Thank you. Good catch, Chris.
So confused for just one
No.
second.
Not that I was trying to do this, but you could do it. But this starts to get into arguments about how, if I had 2 samples, right? And so I said that, and let's say that I wanted to test, again, let's say I'm doing sort of intervention research, right? And I'm saying that I want a stronger test of sort of my waitlist control versus my active treatment group. Now, traditionally, what I would do is I would set up sort of these 2 groups on maybe outcome to be equal to one another. Is that really interesting if they're equal? Or if they're not equal, right? That just means like maybe my one group is a trivial amount more, right? What I could do is I would say, if I wanted to say any difference greater than a difference of, say, no difference to 5-point difference in my 5-point lower in my treatment group relative to my other group is not going to be relevant. I could set up my null hypothesis to test that. I could say so that the difference between my treatment group and my control group is equal to -5, right? And so then I can run through and I can run the same null hypotheses, and I'm saying anything that would suggest, if a plausible estimate of, sort of based on the data that I have, has anything close to less than a 5-point decrease across these two groups, then it doesn't matter if the point estimate says that they're sort of 10 points. If we go through and capture that, so we can go through and start to change this stuff. And this is where arguments will start to be made for point estimates that aren't the null, right? And this is where, when I talked about before, people making arguments for using what they call a thick null, right? So anything that falls within these bounds, we're going to treat that the same as a null value anyway, right? And that's kind of some of the stuff there. This was a friggin' mistake. I didn't catch this, but sort of wanting to know that you don't, like, Zeus isn't going to come down and smite you if, like, you decided that you want something that's not equal to 0 there. Okay. It's like calling your shot. I mean, it would be a strong move. Like, that's a gangster move if you just said, like, look, like, this is what I'm going to do, but it would be pretty compelling, right? Okay. So, and as long as you did that before you knew what the results were going to tell you, not after, right? That's what happened. Like, well, boy, I could sort of start playing around. It's like, how much could I? And then sort of, yeah, I said no more than 5. After I've already seen and sort of know what the answer is with that stuff, right? Okay, does it make some sense? Questions about sort of working through this stuff? All right, cool. So one last thing in terms of thinking about problems. What if our variances aren't equal? Right? What happens if our variances are sort of based on the data that we've collected? It looks like the population variance in my two populations are different than one another. What do I do then? The problem is that we're concerned that the sampling distribution of our test statistic, if we violate this homogeneity of variance assumption, then the distribution of our t statistics that we get sampling from two populations with different variances, the distribution of my t statistic doesn't follow a t distribution. It follows a different distribution. And I don't know what that distribution is. If I don't know what that distribution is, it makes it hard. I can't just start comparing things against our typical t family because I'm going to be off. Like, the distribution that I'm assuming isn't the distribution that is actually taking place. And so in this case, we'll call this t prime. If we're comparing t prime against a distribution of t, all of a sudden all the probability estimates and our confidence starts to get weaker, right? So some solutions. There are, so Behrens-Fisher solution, is having a small collection of table distributions for t, just for a limited number of specific distributions. I mean, if you think about all the different ways two populations could differ in terms of variance, and then also in terms of how they could differ in terms of degrees of freedom, that's an infinite number of possibilities, and it's impossible to table all of them. Behrens-Fisher has a limited number of distributions, but in terms of practical applications, for most of us, this isn't probably reasonable. So what we have instead, and this is what SPSS institutes and most statistical software institutes, a Welch-Satterthwaite solution. And so with the Welch-Satterthwaite, what we're doing is we're assuming that t prime, right, the test distribution of the test statistic drawn from populations with unequal variances, we're assuming that that distribution is a part of the t family. We just don't know what the degrees of freedom are for that, right? So we're saying that t prime does follow a t distribution. It just doesn't follow the t distribution that we would expect given the degrees of freedom. And so what we do with this is we test, if we determine that our populations have unequal variances, we run a corrected test where we're estimating the corrected degrees of freedom based on the sample, or based on the function of variances and the sample sizes in each group. And what we'll see here when we assume unequal variances is we'll start to see test statistics with degrees of freedom that are point values. So it's 19.8 something degrees of freedom. And so it's just a correction on sort of the degrees of freedom that give us an adjustment on those probability values. Okay. We'll kind of understand what's kind of going on with our correction here. Okay, we're assuming that t prime is still following some sort of t distribution. We're just not sure exactly what it is. We just know that it's not the t distribution it's supposed to be following, and so we're just comparing that against a t distribution that we've with a degree of freedom that we've estimated based on the variance in the sample size. Okay? So our big test to determine whether or not we have a violation of homogeneity variance, we'll see is Levine's test, is what's incorporated in most statistical packages when we're looking at some of these violation of this assumptions. What we do with Levine's test is it goes through and it means let's say we've got X1 and X2, right? We've got 60, 75, 73, down, and here we've got 55, 20, 98. Now, based on these two, just that small set of data, which one of these groups are we expecting has more variability in their outcomes? 2, right? So what Levine's test is doing is it's going to go through and it's going to replace each score with its deviation from the sample mean, right? So you're going to have a deviation score. Let's say this is the sample mean is 75. Right? So let's say this is negative 15, and this is 0. That's negative 2, right? And then here, let's say this has 75 as a mean, so we got negative 20, negative 55, plus 3. Okay, right? And what we're going to go through is we're going to replace each one of these scores with its deviation scores. We'll take the absolute value or the mean or the squared score, and then what we're going to do is we're going to sum up all those deviation scores, and then we're just basically going to run an independent sample t-test across those two. Okay, and we're assuming that if we've not violated homogeneity of variance, that the mean deviation score here and the mean deviation score here, if we subtract those two, they should be around 0. If they're not, we're going to say that we've got a violation of homogeneity of variance. So Levine's test, so with Levine's test, are we hoping to reject the null or not hoping to reject the null? Yeah, we're hoping to not reject the null. All right, we're hoping that the sum of the absolute deviation scores in this group and this group is something close to 0, or at least not so far away from the 0 that we say, yeah, these two variances probably aren't equal to one another, right? So this is going to be tricky when we're interpreting Levine's test. Usually we're friggin' jazzed about rejecting the null hypotheses. With this, we're not, right? So if we reject the null hypotheses, it suggests that we may have a violation of homogeneity variance that we have to go through and account for some of that stuff. All right. So what happens if we do start to violate assumptions? Because we will. We're not working in a mathematical or sort of a vacuum where everything sort of conforms to what we'd hope it to do, right? And so we're often going to find that our data don't conform to what we would hope underneath the underlying assumptions of our test. The good news is, particularly for our means-based comparisons, a lot of these tests should be fairly robust to actually some pretty severe sort of violations of things. If I violate my homogeneity of variance test, right? If I have samples with unequal variances, as long as I have relatively equal sample sizes, my tests are fairly robust to that. I'm not too concerned about that. I mean, it's not great. I wish it didn't happen, but it did, and so I'm stuck with that. And so if I have relatively equal sample sizes, violations of homogeneity of variance aren't too bad. If I have non-normality in my scores, right? Again, that's not too big of a deal because, again, what's the assumption of my test? Is it about the distribution of my scores? What is it about? Close, not the population distribution. What distribution am I assuming? Distribution of sample means, remember? So the distribution of my observed scores is the distribution of sample means. And so, yes, if my population distribution is normal, I'm assuming that my sampling distribution will be normal. If I've got reasonably sized samples, that's sort of going to be okay. So if I have sort of weird data, right, so my data are kind of skewed, as long as I've got a reasonable sized sample, and my distributions are similarly shaped. So Chris C, you're looking at some stuff, and you've got sample one, you got a pretty sort of reasonable skew in sample one, but you've also got a reasonable skew in sample two that looks about the same. You got reasonably sized samples, so you got cell sizes of say 40, you're going to be okay, so probably not too much of a problem, right? Where we start to get in trouble is when we start doubling down on violations, right? So if my data have different shape and unequal variance, right? So if I've got something like this, sample one has a positive skew, sample two has a negative skew, and the variances are clearly not equal in that across these, I've got some problems. I'm probably going to have, starting to have some questions about sort of the validity of my inferences for my t-test. If I have unequal variances and unequal sample sizes, right? So my data look kind of normal, but I've got wildly discrepant, like I've got a wildly unbalanced design, and my homogeneity variance in tests come up as positive. If my larger sample has a larger variance, I'm going to have too conservative a test. Someone tell me why. What do you think, CJ? If I've got an unbalanced design, I've got 15 people in sample one and 100 people in sample two, and my sample with 100 people have larger variance, why am I going to end up with too conservative of a test?
I'm not sure. Isn't it kind of weird that your large sample has a larger variance?
Well, there's a lot of reasons. At the end of the day, they're different populations. So, they're different populations. They could have wildly different variances. Right? So the assumption is that they're equal. So what I'm going to do is if they have unequal cell sizes, I'm going to pool the variance. Well, which sample, 15 or 100, is going to carry most of the weight and determine what the final variance is? 100, right? And if that's the sample that's got a much larger variance, that means my pooled variance is going to be really high. And when my pooled variance is high tomorrow, what does this do to my standard error? It increases it, and what does that do to my test statistic? Makes it smaller. So I'm going to end up with a more conservative test than I might otherwise expect. On the other hand, if my larger sample has a smaller variance, my sample of 100 has like a fifth of the variance as my smaller sample. Again, that larger sample is playing a much larger role in determining my final pooled estimate, and then that pooled estimate is going to be considerably smaller. And so what's the concern is I've got far too little of a test under that circumstance. Okay? If I've got violations of normality and small sample sizes, I've also got problems here. If my data are crazy weird, right, and sometimes we collect stuff, again, substance use is just a good example of stuff that offer measures that often don't have normal distributions. If you've got sample sizes 25, 30, it'd be nice if they're bigger, but they're still, for means-based comparisons, probably not too bad. But if I'm working with 10, 15, and I've got crazy skewed distributions, I'm going to have to probably start to be concerned about the potential impact on my tests. Okay. So again, our means-based tests are pretty robust. They handle, they can take a lot of damage until we start doubling down on stuff, and then that's when things start to fall apart. Okay, but it's nice to know with any type of thing, the potential impact of violations on your outcome. That can start to help you understand what's going on when you do get your results, right? So if I have a wildly unbalanced design, let's say I'm only looking at people with psychopathy, and so I was able to get 15 students there, and people without psychopathy, and I got 100 students there, right? And I know that my larger set, my normal students have a much higher variability in whatever it is the outcome, and I get something that's sort of kind of marginal, like 0.04, p equals 0.04 or something like that. I can sort of interpret that, but then I can say, well, sort of based on sort of violations, homogeneity of variance, and my unequal sample sizes, I'm expecting this to actually be a fairly conservative estimate of the difference between these based on what's going on, right? And so I can start to use information about this to then sort of evaluate my results in context and things along those lines. And so this is in that last section in your write-up for your screening. These are the types of things that I sort of want you to be. It's easy to say, to point out what's wrong. Like, oh, that is that, and this is that. One, to think carefully about the potential impacts on your data to help you sort of understand it a little bit better. Questions about this? Okay, cool. So we'll finish up with screening for independent sample T. You can go through, and if you don't have it pulled up already, your data set MBA t-tests. What we're interested here in this hypothetical study is gender differences in marital satisfaction in motor vehicle accident survivors committed to long-term heterosexual relationships. We've got 22 men, 22 women, 5 men needing diagnostic criteria for PTSD. Subsequent to motor vehicle accident, completed the Lock-Wallace marital adjustment test. Scores range from 2 to 158. Higher scores indicate greater relationship satisfaction. We also gave participants the Marlowe Crown, right? Look at differences towards socially desirable responding in men and women, right? If we see a difference, basically we want to make sure it's not functioning just like one group is responding in more socially desirable fashion than another. Based on previous research, investigators hypothesized that women will report greater levels of marital satisfaction than men. Tendency towards socially desirable responding expected to be similar across groups. So if you pull up your data set and grab your handout here, your independent sample t-test screening. So what we're going to do in SPSS, and this is just kind of easy to do here, and it's a small set, so we already know we've got some issues going on here, right? Here I see I have a missing value for 2 scores. If I go through and I click on this column, and I right-click, and I hit sort ascending, that's just a quick way to see what missing data I have, because anything missing is going to come right up to the top, and I can see that I do have, for case 132, and if I'm looking at gender, what does gender 2 mean if I go to my variable view? Okay, so I've got a woman in my sample who has not reported a marital satisfaction score or a social desirability measure, right? So what I would do is I would make a note on my, sort of whatever I'm using to keep track of my screening, that I'm going to get rid of case number 132, female participant, and we got rid of her because she didn't have was missing values, right? So document that. If I go through and right-click and hit clear, that'll get rid of that stuff there. Okay. So again, if I'm looking at my handout here, and I'm seeing that Lock-Wallace ranges from 2 to 158. So here's my low value, here's my high value. See that everything fits there. Same thing if I do this with my Marlowe Crown. Marlowe Crown ranges 0 to 33, 0 to 26. Okay, everything's kind of in balance. So I know at least when I'm jumping into stuff that my scores that I've observed are at least making sense. What I'm going to do to start out with is I want to go through and take a look at my distributions. I'm going to analyze descriptives, descriptive statistics down to descriptives. Here I am interested in my Lock-Wallace and my, actually, wait. Well, let's do this first. Lock-Wallace, Marlowe Crown, kick that over. Options, skew kurtosis, continue. And I want to save standardized values as Z values. So I want all that stuff, I want to make sure that I've got all that. Okay, and then I'm going to go through, I'm going to hit paste. Okay. So here is going to give me my syntax just for looking at my distribution of scores. Now I could run this. Why shouldn't I run this quite yet?
Because you care about the gender differences.
Perfect, yeah, I care about gender differences, right? If I go through and I look at distributions, and I look at z-scores, it's gonna be giving me z-scores based on the mean of the entire set of scores, right? And that's not what I'm interested in, right? When I'm going through and I'm looking at my distributions for my independent sample t-test, I need to look at these separately within men and within women. An extreme score in men might not be an extreme score in women, right? It might be sort of right, dead set in the middle, right? And so we need to make sure that we go through and split the file. So what we're gonna do is we're gonna go to data, down to split file. In split file, we are going to compare groups. You can hit organize groups by output, I just like compare better. But what we're gonna do is we're gonna throw in our grouping variable. So we're gonna compare groups based on gender, and we go through, we're gonna hit paste. Okay. Over my syntax file, I'm gonna copy that. I want to put that first. Okay. So when I run this sort file, what this is gonna do is it's told me, okay, I've gone through and sorted everything by gender. Okay. And now, until I go through and I sort this data, anything that I do in SPSS is going to give me separate output for men and separate output for women. If I sort it, then it turns the split file off. But as long as I'm just running stuff, it'll give me separate results for each group. So if I go down to descriptives and I run my descriptives here, take a look at my outcome, I see that yes, in fact, SPSS has separated this into results for the Locke-Wallace and the Marlowe-Crown for my men, and for the Locke-Wallace, Marlowe-Crown for my women. This tells me it's done sort of everything that I want it to do here. Okay. So Siley, tell me what we're seeing. What are you noticing based on descriptive statistics for these two groups?
Mine is having issues, that's why I'm looking over here, but.
Okay. Based on your handout is the same stuff as up here too.
There is a skew in the women, so there's -52 for the women.
Okay, so you have some skew and there's a Locke-Wallace for the women, right?
And then for the MC as well.
Yeah.
More
Okay.
And then,
So we do have, so our skew's not 0.
yeah.
Are we concerned about this level of skew? Probably not. Of our skew and kurtosis values, which one of these might start to flag as maybe more problematic?
The kurtosis values for men.
Kurtosis values for men. Now, again, general rule of thumb, right, is skew kurtosis less than 2 is sort of fine. Kurtosis actually gets sort of higher, but again, this might start to, like, I might sort of take a closer look at this, right? I've got kurtosis values greater than 2, and I've got negative kurtosis values. Nick, what does this tell me about the distribution of negative kurtosis? Yeah, it's flat. It's kind of boxy. It's kind of flat, right? Kind of sort of rounded humped shoulders there, right? What else is going on across these groups that I should probably be paying attention to? Yeah.
The sample size.
Yeah. Yeah. What's going on with sample size?
You have fewer men by a factor of 4.
Yeah. So I've got about 4 times as many women as men, right? And so I've got at the very least an unbalanced design. What else am I concerned about there in terms of sample size? Particularly with men.
That's all I got.
Okay. You and Chris? Or excuse me, CJ?
It's just small.
Yeah. How small?
That varies.
5 small, right? That's not much of not much of a sample of anything. Okay, so already off the bat, I'm concerned about whether or not I have enough power or sort of enough people to do much of anything here. Like this is a very, very, very small sample. It's unbalanced, but I've also got, I only got 5 men in my sample, and so already I'm starting to become fairly skeptical about this. But, so what I might do is I sort of note this unbalanced sample, and sort of note large, sort of high elevated levels of negative kurtosis among the men. But what we're going to go down through is take a look at this in terms of sort of graphically what this distribution looks like. So what we're going to do is first go back to your data and go to subject, right click, and sort ascending. Okay. Why did I do this? Guesses tomorrow? What did I say sort undoes? Turns my split file off. Okay. So what I'm going to do is I'm going to go up to Analyze, go to Descriptive Statistics, and I'm going to go down to Explore. And hit Explore. And so my dependent list, this is the stuff that I'm interested in. So I'm interested in the Locke-Wallace and the Marlowe-Crown. And then what I'm going to do is I want SPSS to give me both of these scores by gender. So I'm telling SPSS to split this up by gender. And then also this subject number here, I'm going to go down and drop it into label cases. What this is going to do is if I have on my box plots, if I have values that are beyond 1.5 times the interquartile range, it'll start labeling those values with the subject number. If I don't put that in, it'll still attach a label to those, except the label that it will attach is just the case number, right? And so it's easy to get that confused back. Well, case 15 did this, but well, that's not case 15, that's case 339, right? But if you just put subject number down there, it'll start labeling extreme values in your box plots with the actual subject number that you put in. So we're going to go down, so we've got that, we're going to hit plots, we're going to check histogram, we're going to turn off stem and leaf. Stem and leaf plots are nice, but we won't worry about them right now. I'm going to hit continue, and I'm going to hit paste. Okay. Now, we've got this examine command that's going to go through and it's going to split Locke-Wallace and Marlowe-Crown up by across men and women. If I try and run this with the split file still on, I'll just get an error message because it can't split by gender if it's just looking at men and women separately. So I got to turn that off. It'll happen, like you'll try and run this and it'll give you an error message. It probably just means that you've still got a split file on. Okay. So if we go through and we run this, think about it, it's time to do it. Oh, just thinking about things. Computer sounds like it's gonna blow up. Okay, well, I don't got time to wait for it to run simple stuff. Take a look at your handout here. Oh, okay, here we go. Sorry, I just had to sort of publicly shame it, and then it's like, okay, fine. All right, so here we've got histogram for men. Chrissy, what are we seeing in the histogram for men?
We're seeing a pretty big difference in scores for the Locke-Wallace.
Yeah. I mean, I would say we're seeing that we have 5 values, right? I mean, and this is the thing, like it's, so we saw the negative kurtosis there, right? And like, if you had a sample of, say, 50 or 100, I would be curious, and so I wanted to sort of kind of see what this looks like. But with only 5 observations in here, like we're big distributions. I mean, the good news is it's not obviously non-normal, right? There's nothing to suggest that that group of 5 scores wouldn't, the distribution of sample means wouldn't eventually sort of turn into, and we did that demonstration where we had just the 4 values and sort of this sampling still distribution still turns in, but it's really small, right? So we might sort of note that the non-normality that we're seeing among the males these across these 2 things is because there's only 5 values there, right? Women, we're seeing maybe a little bit of a negative skew, in terms of the Loch Wallace, but actually kind of looks like maybe a bimodal thing going on there, which is kind of interesting, right? I mean, if anytime I see something, I don't want to read too much into it, but anytime I see bimodal distributions, I'm wondering if I'm getting kind of two unique populations. And if marital satisfaction, this might be people who have strong relationships and people who have some difficulties, and so they're kind of looking at some stuff, but at least in terms of just raw, whether or not this is causing problems for my distribution, I'm not too worried about it, probably. Box plots for my Loch Wallace across men and women. That's about as symmetrical for men. I mean, they've got 5 values, right? There's a 1 value, 2 value, 3 values, 4 value, 5. That's just kind of what's happening. But for my women, again, sort of medians, sort of differences there, right? So already, just looking at median values, it looks like maybe some support for my hypothesis, and that at least the median value among women is higher than among men. Down, same type of thing for my Marlowe crown. I can't really tell much about that. That's what distribution with 5 people in a room will look like, right? So I wouldn't read too much into that kurtosis value. Again, among women, seeing some negative tail, maybe-ish, right? And if we look at our skew values, but have skew of negative 0.5-ish for the women in both states, and this is kind of what's captured there. And then my Marlowe crown for men, again, kind of got a fat lower end on the box plot here, so the women's, but again, nothing too outstanding, right? Nothing too crazy. All right. So the last thing I would do, again, I can go down and go to analyze descriptives, and this time kick out my, actually, do this. I want to go back through because I want to split up, I want to take my look at my z-scores, and I want to split this up again across men and women. So I'm going to copy my my split file command back up here. And then what I can do is I can take this descriptives, and I can copy that, and paste it again down here. And I can do this through the pull-down menu if I wanted, but it's just easier if I go through these SPSS, those z-scores that I created. Remember that I split those files before I ran that initial descriptives. So what it did is it ran my z-scores specifically for women and specifically for men. Now, if you don't split the file before you do this, you're just going to run z-scores based on the mean of the whole sample, and things are going to be off. So you got to make sure that you run those descriptives, that you split the file before you run the descriptives overall. But what I'm going to do is now I'm going to go through and I'm going to split the file again. This time I'm going to look for the z-score of my Loch Wallace, z-score for my Marlowe crown. You see those values right there. Again, SPSS just drops a z in front of it. I can erase this save command because I don't need it to save z-scores on my z-scores. I'm also not particularly curious about my skew and kurtosis for my z-scores because those are going to be the same as the skew and kurtosis for my regular distribution. And so just kind of run this from here. Okay. So if I go through, split my file, and ask for the descriptors on my z statistics for men and women, what I'm going to get here is my z table. And Chris, what am I seeing in terms of my z-scores here?
They are, let's see.
Yeah. Am I seeing anything that sort of makes me nervous about anything here in terms of extreme values? No, not too much, right? Again, rule of thumb, if I'm seeing z-scores, I mean, if you want to attach it to a p-value of 0.001, then we're talking about a z-score that exceeds plus or minus 3.29, right? We've got a small sample here. I've got, so 4 women on my Marlowe crown. I've got at least 1 woman who's scoring close to 2 standard deviations below the mean. But in general, given my distributions and graphically what's going on, there's nothing in here that's going to cause me a great deal of concern in terms of an extreme value for anything here. So if I go through, and if you grab your handout, for your screening example for the independent sample t-test, so we see we've got missing value for Lock Wallace total and Narrow Crown for case number 132. So noting that that's yeah, it's just this one sheet. It's the screening output stuff. So one score that we had to kick out, just wanting to note that that was a woman, that female participant for that. No evidence of problematic values. Got rid of the missing case with missing values, would give us a reduced set of 26. Talking about distributions for men, distributions for women, kind of just going through and giving a description of the sample and kind of what's going on, noting that the male sample has notable kurtosis, but if I look at histograms, say that that's probably due to sort of the fact that I only have 5 people in there. Women looking pretty good. So this, you see under women, I say box plots were unremarkable. If you're going to say something's unremarkable, make sure that it's unremarkable. Don't just call everything unremarkable, because I know there's weird stuff going on in this stuff, right? Extreme values, data provide strong evidence for univariate outliers for Lock Wallace and Mortal Combat. Marlowe Crown scores in male or female samples. You'll notice here that I'm using absolute values, but still including the negatives in there. I think this is just telling you which direction the high values or the peak values are going, whether it's below the mean or above the mean. So something to incorporate there. Homogeneity, we didn't get into homogeneity variance, so we get into that, sort of possible stuff going on, and then writing things up. Okay, so again, use these as an example or a guideline. People are often intimidated of the whole screening process. For each one of our examples, I'm going to go through and give you sort of things to look at, so you kind of see how we're framing this stuff, so that we can move forward. Okay. All right, nice work, folks. How are we feeling about all this stuff? Doing all right? Okay. Hopefully, a lot of this is review. It's just sort of a more in-depth look at the types of things you were maybe introduced to in previous classes. Just getting a little bit more into the nuts and bolts of stuff, but.